how fast would I have to jump to not come back down to Earth? The answer? 11.2 kilometers per second. This is known as escape velocity. But what's that got to do with black holes? And what do black holes have to do with this year's Nobel Prize? The answer to both in just a moment. So, did this photo win a Nobel Prize? Short answer, no, but it is related. But before we get to it, let's look at what black holes actually are. And for that, we're going to look at the first half of the Nobel Prize awarded to Roger Penrose for proving that black holes were actually possible. And this was no easy feat, as they're just weird. Remember me jumping earlier? Well, now imagine I'm standing on Jupiter. How fast would I have to jump to not come back down now? I mean, assuming that I've got a spacesuit and ignoring the fact that the planet is made of gas. Well, I'd now need to jump at 60 kilometers per second. You see, I need more energy to escape the stronger pull of Jupiter's mass. So, if we keep increasing the pull of gravity, I just need to jump faster and faster, right? Well, there's a problem. C, the universe's speed limit, the speed of light. Once you reach the speed of light, we get what's known as an event horizon, and nothing inside can escape. This raises an important question. What happens if I stick my hand in a black hole? Well, things get tricky. As my hand approaches the black hole, assuming it doesn't get spaghettified, and yes, that's the correct term for being ripped apart by gravity, then as it gets closer, it'll go red and then slowly fade from view. From my perspective, time for my hand slows down and it never quite crosses the event horizon. But if I somehow could put my hand inside the black hole, then it's now in my future. And to get it out, I would need to reverse time. Confusing, right? Yet, as I've mentioned in a previous video, black holes do in fact have a temperature, so radiation can get out. Just not my hand. And if this all seems too weird to be true, then you're not the only one. Even Einstein described the idea as not convincing in a 1939 paper. So, along comes Roger Penrose, who, by developing new mathematics and addressing the theory of general relativity, in a 1965 paper proved that black holes not only are possible, but are an expected phenomena in our universe. So, how do you observe something that you can't see? Well, you don't. Not directly, at least. Instead, you look for objects near black holes. You look for bright stellar bodies orbiting seemingly invisible object. And that's where the other two Nobel laureates come in. Reinhard Genzel and Andrea Ghez studied the orbits of stars around black holes. In particular, they turned their telescopes to the center of our galaxy and managed to track a number of stars. By mapping out their orbital paths, they could not only figure out where the black hole is, but they could also figure out its size. And what they found was massive. So big that it got called a supermassive compact object. Sorry, scientists aren't always the most creative with names. This invisible object at the center of our galaxy was 4 million solar masses, or 4 million times the size of our sun. Even for a black hole, that's huge. Stellar black holes tend to have a mass of about 10 to 100 times bigger than our sun. And that brings us round full circle to this photo. It's of a supermassive black hole, but not from our galaxy, from M87, and is in fact of a black hole 6.5 billion times the size of our sun. Black holes are still seemingly alien to us in many ways. Yet, because of these scientists, their teams and their collaborators, we now know a bit more about the universe that surrounds us, no matter how strange it gets. And hopefully, this is just the beginning of humanity's journey into the invisible. Remember, I'm almost a doctor, and until next time, be like a proton. Stay positive.